to understand where we are, we have to travel back to 1972. Imagine a world where computers were still largely the size of refrigerators, locked away in climate-controlled rooms.
Then came the Intel 8008. It wasn't just a successor to the 4004.
It was a manifesto. While the 4004 was a humble 4-bit calculator on a chip, the 8008 stepped into the ring as an 8-bit powerhouse. Now, why does that matter to you? Think of it like a language. If the 4004 spoke in simple grunts, the 8008 was starting to form full sentences. It had a larger addressing capacity, which is just a fancy way of saying it had a bigger memory palace to store information. But the real magic, the thing that changed the DNA of programming, was indirect addressing. In the early days, if you wanted the computer to find something, you had to give it the exact address every single time. It was like giving someone directions by saying, "Go to 123 Maple Street." With indirect addressing, you could say, "Go to the address written on the piece of paper in my pocket." This allowed for vector tables and complex data structures. It allowed software to become flexible. As we move deeper into the 70s, we encounter a concept that defines your daily life: the interrupt. Before interrupts, a CPU was like a very stubborn person who wouldn't listen to you until they finished their current task. If you pressed a key, the CPU might not notice because it was busy calculating a math problem. This is called polling, and it's incredibly inefficient. Interrupts changed the game. They allowed the hardware to literally scream, "Hey, stop what you're doing! I just clicked the mouse." The CPU would pause, save its place, handle the request, and then jump back to its work. This is the bedrock of multitasking. When you are typing a document while music plays in the background and a file downloads, you are witnessing a million tiny interrupts happening every second. By 1974, Intel released the 8080, and this was the Big Bang moment. If the 8008 was a prototype for the future, the 8080 was the future arriving on your doorstep. It had higher clock speeds and expanded addressing. It could talk to external devices through an I/O bus, making it the heart of the first popular personal computer, the Altair 8800. But success breeds shadows. Former Intel engineers led by Federico Fagan felt they could do better. They left and formed Zilog, creating the Z80. The Z80 was like the 8080 but on steroids. It was faster, cheaper, and more compatible. This competition forced Intel to stop resting on its laurels. This is the iron sharpens iron principle. Without the Z80 pushing from behind, Intel might have slowed down. In your own career or life, don't fear the competition. However, even giants stumble. Intel tried to leapfrog the entire industry with a project called the iAPX 432. They wanted to create a radical 32-bit architecture that handled objects and high-level languages directly in the hardware. It was incredibly ambitious. It was a Starship enterprise built with 1970s tools. The project was a disaster. It was too slow, too complex, and it ignored the practical needs of the market. This is a profound lesson for all of us. Innovation without practicality is just an expensive hobby. Sometimes we get so caught up in the perfect version of our dreams that we fail to deliver the useful version. Intel realized they were losing ground because they were chasing a ghost, so they pivoted. They put a small team together to build something grounded, something compatible, and something fast. That pivot saved the company and gave us the 8086. In 1978, the Intel 8086 was born. This wasn't just a chip. It was the birth of an empire. It was a fully 16-bit processor, meaning it could handle much larger chunks of data at once. It introduced segmented memory, a way of tricking the system into accessing more than 64 kilobytes of RAM by dividing it into segments. While some programmers hated it because it was messy, it allowed the 8086 to address a full megabyte of memory, a massive amount at the time. It also introduced prefetching. The CPU would look ahead and grab the next instructions while it was still working on the current one. It was like a chef's assistant chopping onions for the next step while the chef is still sauteing the garlic. The 8086 also solidified the use of the stack. This is a memory structure where you push data on top and pop it off later. It allowed for structured programming and subroutines. But it also introduced the stack overflow, that dreaded moment when you push too much onto the pile and the system crashes. As the 8086 took over, a philosophical divide emerged: CISC versus RISC. Intel stood for CISC, complex instruction set computing. The idea was to make the hardware do the heavy lifting. One instruction could do a lot of things. This saved precious memory because the programs were shorter.
On the other side was RISC, reduced instruction set computing.
They argued that instructions should be simple and lightning fast. This was the high-level versus low-level debate of the century. CISC was like a Swiss Army knife one tool with many blades. RISC was like a set of professional scalpels. Each does only one thing, but it does it perfectly. What's fascinating is that over decades, these two philosophies merged. Today's chips are hybrids. They look like CISC on the outside to keep old software running. But on the inside, they break those complex instructions down into tiny RISC-like micro-ops. We often talk about the CPU as the brain, but even a brain needs a calculator. Intel introduced the 8087, a math coprocessor. It sat next to the CPU and handled the heavy floating-point math decimals, trigonometry, and big number crunching. This was the first time we saw specialization in microcomputing. By offloading the hard math to a specialist, the main CPU could focus on running the program. Everything we've discussed culminated in 1981. IBM, the Blue Giant, decided to build a personal computer. They chose a variation of the 8086 called the 8088. They chose it because it was 16-bit on the inside but could talk to cheaper 8-bit parts on the outside. It was a compromise that changed history.
IBM's decision to use Intel-S chip and Microsoft's operating system MS-DOS created a standard.
Suddenly, it didn't matter who made the computer. If it was IBM compatible, it could run the same software. This created the PC revolution. It made Bill Gates the richest man in the world and Intel the king of the mountain. But notice the pattern. IBM didn't invent the chip, and Microsoft didn't even invent the OS. They bought it and refined it. They standardized it. Power doesn't always go to the person who invents the thing.
It goes to the person who makes the thing accessible to everyone.
Today, as you sit with your multi-core laptop, you are essentially using a direct descendant of the 1978 Intel 8086. x86 architecture is the longest-running dynasty in tech history. Every time you open a window or click a link, you are utilizing segments, interrupts, and stacks that were refined in the disco era. The DNA of those early engineers is still alive. Their mistakes, their pivots, and their flashes of genius are literally etched into the hardware you are using right now. It reminds us that nothing we do is truly lost. The foundation you build today, even if it seems small or 8-bit, might be the structure someone else builds a skyscraper on 50 years from now. If there is one lesson to take away from the expanding story of the CPU, it is this: evolution is messy, but compatibility is king. Intel won not because they always had the fastest chips, they often didn't, but because they made sure that the work you did yesterday still worked on the machine you bought tomorrow. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.